Welcome to AI for Arts and Humanities, as Will said, curated by the Turing Institute, the UK's National Institute for Data Science and AI. I'm David Beavan, Senior Research Software Engineer in the Research Engineering Group at the Turing, and I'm a co-organiser of the Humanities and Data Science Turing Interest Group. And I'm very, very pleased to be your host today. Today, you'll hear from 1001 enthusiastic and knowledgeable speakers, and that's 9 if you're not counting in binary. First up, some introductions from the Arts and AI and Humanities and Data Science Turing interest groups, who have curated this amazing lineup and are always on the lookout for new partnerships. Then the main event of 4 in-depth talks showcasing the challenges and opportunities for AI in the arts and humanities. After the hour, for those with access, join us in the Q&A session that follows for 3 lightning talks discussing the diversity of artistic and humanistic work with AI, followed by the Q&A panel chaired by Dave Roure, where you can really quiz the headline speakers. So, if you're sitting comfortably, then we'll begin. First up, I'd like to introduce to you all Barbara McGillivray, who is Research Fellow at the University of Cambridge and a Turing Research Fellow. Alongside Barbara is Miguel Rodrigues, Professor of Information Theory and Processing at University College London, and also a Turing Fellow. Both of them are about to tell you all about the Turing's leadership in AI for Arts and Humanities and the 2 special interest groups. Barbara, Miguel, over to you.
So I'm going to say a few words about the humanities and AI, and then Miguel will follow shortly. So when we think about humanities, we often think of a researcher sitting in a library reading lots of books or analyzing objects, and we don't necessarily think about AI. But AI can give a lot to humanities and vice versa. And there are various ways in which this can happen. You can think of automatic methods for doing research in the humanities in new ways, and you'll hear more about that in the talks that will follow. But there's also a lot of work in infrastructure and creating the right infrastructure for doing humanities research at scale. Humanities researchers can also help AI in giving it the historical and critical background. There's a lot of talk around ethics and philosophy of AI, and humanists are best placed to contribute in that way. And finally, there is the whole world of algorithmic creativity, which of course interfaces very directly with the AI and arts. So back in 2017, I initiated this special interest group called Humanities and Data Science at the Alan Turing Institute, which has grown to more than 70 members and affiliates, involving all the partner universities of the Alan Turing Institute, plus other great institutions like British Library, National Library of Scotland, and the National Archives. And we've organized lots of events and activities, including a white paper that is coming up soon, and panel and hackathon with the National Archives back in December. So stay in touch with us. These are the names of the organizers of the group, me, Alex, and David Beavan. We have a mailing list and Twitter hashtag, so always happy to have new collaborators and partners. Over to Miguel.
All right. Thank you so much, Barbara. Now, in the same way that AI has been playing a role in the humanities, there's also been a cross-pollination of ideas between artificial intelligence and the arts in general. And in particular, so we have been seeing a number of ways whereby AI has been feeding into the arts and vice versa. So one of them is on the use of AI to support art conservation, preservation, but also art historical investigation. And currently we are at a stage where we can capture very rich data sets associated with paintings. And by leveraging these data sets together with sophisticated artificial intelligence techniques, we can develop new means to inform art conservation, preservation, but also curation of art. The second way whereby AI has also been interfacing with the arts is via art generation and also algorithmic creativity. And this is just an example of a painting that has been generated by sophisticated artificial intelligence techniques that went to sell and sold, in fact, by far much more than it was initially expected. So it beat all the expectations. So artists are now beginning to embrace some of these techniques. And another way whereby AI and the arts have been exchanging ideas is, for example, within the context of performance arts. Now, in recognition of this interplay, also the Turing and a number of people in the Turing have decided last year to found a new interest group that is positioned at the interface between artificial intelligence and the arts. And this group discusses a number of topics, such as, for example, AI and arts practice, the role of artificial intelligence in cultural heritage, in the creative industries, but also, for example, AI in cultural policy. So we are now beginning to put this group together. So we are engaging with a number of partners from the Turing network, outside partners, in particular cultural heritage institutions. And we organize a number of activities ranging from seminars to webinars, and there's much more planned out for this year and the upcoming ones. So if you're interested in the interplay between artificial intelligence and the arts in general, please feel free to get in touch to discuss possibilities. So what you will hear next is a number of talks that we have curated by leading experts and renowned individuals within this field. And I'll pass the word down to David once again, who will be able to introduce our various speakers.
Thank you, Barbara. Thank you, Miguel. And everybody check out the Turing webpage. Look for the 2 special interest groups there online. David, it is my absolute pleasure to introduce you to the world. So this is Dave de Roure, Professor of E-Research at the University of Oxford. And Dave is also a Turing Fellow. Take it away, please.
Thank you, Dave from the Turing. I'm just going to show my screen. There we are. So thank you so much for inviting me to speak in this session. In fact, I attended CogX last year and spoke in the related session, the creation of the group, the special interest group on art AI, occurred just after that. And I guess I'm addressing both here, the humanities and data science and the AI for arts groups, and I have the privilege of being involved in both in the Turing. I'm also presenting work that's from my Turing project. I'm a Turing Fellow. I've been doing this project for 2 years in collaboration with the Royal Northern College of Music, our Northern Conservatoire, and a group called PRISM, which is the RNCM Centre for Practice and Research in Science and Music. We've also been working with an EPSRC-funded project called FAST, Fusing Audio and Semantic Technologies, which is about using semantic technologies all the way through the music chain, from composition through performance and recording and mixing and production, all the way through to distribution and consumption. So very much about the technology and the music. So thanks to everyone I've collaborated with over the last 2 years. And I'm going to tell you something about the events. First of all, introducing where we were up to a year ago, and then I'll tell you what's happened since then. So when I spoke in the event last year, I focused on Ada Lovelace. Importantly, today held up as an icon of women in computing, as a sort of STEM icon, as it were, because she did this important early collaboration with Charles Babbage, and she published the first computer program, as we know it, in computers today. Now, interestingly, to me, one of the most distinctive things about Ada Lovelace was not just that, but the fact that she could see applications of computers and of computation other than in the things that were of interest back in the 1800s, which was calculations, it was log tables, it was engineering. She could see the applications elsewhere, for example, in music. And she was a musician. People don't talk about that. They talk about her mathematics, but not so much the music. This is an article I published in BBC Music Magazine January last year, which tries to sort of redress this balance of of how Ada Lovelace is seen today to remind everyone about the music. And so not just STEM, but STEAM, definitely an original steampunk icon in my view. She wrote about music and computers in her translator's notes in 1843 to an article by Babbage based on the talk he'd given about the analytical engine. And in that she wrote about the composition of music, of elaborate scientific pieces of music of any degree of complexity or extent. And this is what today we might term algorithmic composition. I talked about it last year, and there's a lot of work going on, has been for many years, in this area. This year, I want to focus on something else that she said, another famous quote from her translator's notes, where she questioned whether computers can be creative by saying the analytical engine has no pretensions to originate anything. It can do whatever we know how to order it to perform. Now, this is an important writing by Lovelace, which has been discussed by Alan Turing, it's been discussed by Margaret Bowden, many others since then. And it's about this, if you like, an axis between humans doing creative things with computers at one end and computers doing things that require creativity in humans at the other end, and that's computational creativity. It's interesting that she wrote a number of things about this. Here's another one of the quotes. The engine is capable under certain circumstances of feeling about to discover which of two or more possible contingencies has occurred. Now, to understand this quote, it needs to be viewed in context. What I find interesting about it is the language. The engine is capable under certain circumstances of feeling about to discover. What we're seeing here is a kind of early anthropomorphism and this sort of study of how humans, as they talk about technology, give it agency, which we're hinting at that here, is a subject of humanistic inquiry, and it's a subject of another project at the Turing. It appears in Living with Machines, which is reanalyzing the Industrial Revolution using the modern data science techniques and looking at the occurrence of agency in popular writing at that time and what we assigned to machines. So today I want to talk more about this issue of creativity. And just after the CogX last year, we had an event in Manchester where we were asking people to determine which bits of music were written by human and which by AI. And this was based on this event by Marcos de Soto at the Barbican last March, where we had a human musician, harpsichord player, performing a composition created by composer Rob Laidlow, who'd been working with AI. He trained the AI on Bach, and he had bits of actual Bach and bits of AI-generated Bach. And as a composer, he wove these things together, transposed them into the same key. He wove them together, and there were a number of transitions back and forth between these. And the audience needed to guess, estimate, see if they could tell the difference between the human and the machine by holding up cards saying human or machine. And we could monitor that. The picture on the left here you see is a shot from the video analysis going on in the Barbican, where it was telling what colour cards people were holding up. The picture on the right from the CogX last year at the Royal Northern catches us partway through. What you see here is the human pianist, in this case, who's been performing Rob's piece. You see Rob about to reveal the right answers. You see Marcos de Soto introducing it, but behind is the image from the camera that's doing the analysis. So the audience is not only saying whether they think it's human or AI at this point, but they're seeing feedback of what the overall audience assessment is. This was run again at the Royal Institution Christmas Lectures at the end of the third lecture. And we have a video clip of that. And this is something you can go away and view because these lectures are publicly available online. After that, we did another major piece of AI work. And so interestingly, those things that we presented so far were about, could people tell the difference between the human and the machine, which is one way of looking at this problem. We moved on to the composer making use of the AI as part of the compositional process. This is an evolution of what Rob had done with the Bach piece. And then we created, as part of an event at the Barbican in November last year, this piece of music called Alter. And this, I think, is significant in the sort of history of contemporary classical music and AI, as this was written about artificial intelligence and also using artificial intelligence to do that. And you can see the quote here from Rob Laidlow. Through 3 phases, it traces the development of an artificial mind from hazy, unformed conception to a complex and creative self. Between each phase, this curious and perfectionist mind dives into its own code to retrain and develop itself. Now, I will just explain to you what went on behind the scenes in this and where this is different from the earlier pieces, which were done using AI techniques like LTSM. We have here used techniques to generate text, which is sung, along with the music. And this rather complex workflow in this diagram explains this little bit of history. So let me just run this through. Again, based on Lovelace, we took the correspondence between Ada Lovelace and Charles Babbage, who we referred to previously, which are kept in the Bodleian Library. And the family papers are on deposit there. Box 170, there we are, some of the papers going in there. Some of this has been made available online in various forms by various biographers, but it also, here we make use of the electronic enlightenment corpus, which is a corpus held by the Bodleian Library, which for our purposes contains a lot of 19th century correspondence. And this enabled us to build a model of the English language of the 19th century, to then train it on the Lovelace Babbage correspondence and then generate text, prompt it and generate text as if written by Ada Lovelace. Now, many AIs used for generating text today are trained on something else. For example, Wikipedia, the English of Wikipedia. It was important to us here that we trained it on that 19th century set. And the sort of the thought experiment in our head is, what was the language that Ada Lovelace grew to learn at that point in time in the early 1800s? What was the literature that she was exposed to? We can have a discussion about whether she'd read Byron or not. And then this was used to generate a sort of ghost of Ada Lovelace fragments of text, which Rob then took into a contemporary AI. So there are 2 AIs in this picture, which is GPT-2, trained on a very large, the largest amount of literature, and that was used to generate the text. I will tell you about this. You can see the picture on the screen on the left-hand side there on the stage in Milton Court Concert Hall. You have members of the British Sinfonia performing this work. You have an interesting thing on the left, which I'll say some more about. We performed this a second time. That was the premiere in November. We performed it a second time in the Hollywood Music Room in Oxford in a programme organised by Torch, the Oxford Research Centre in the Humanities, and Calculus of the Nervous System was the title of the event. But this was the second production of Alta. And again, here you can see the singer and members of the British Sinfonia. You can see also the percussionist with the strange machine at the back. And to the left at the back, you can see Rob Laidlow, the composer, with his laptop, an essential part of the production. So here's an example of the text that was produced during the ongoing training of the AI during this performance. So the earlier part here, I cannot explain this step, but I have altered my mind. It seems to me as clear as possible.
David, would you like to wrap it up on your next sort of comments, please?
I'm just coming at the end, Dave. Thank you. Yeah. And as the training went on, we get these interesting reflexive comments. What is the nature of the body? Am not I pure? Am not I a noble person? Am I beautiful? Am I not a man? The thing is a thing of wonder. See here how we've used the text. And if you look at the RNCM Prism website or Rob Laidlow's YouTube channel, you will find the video of this performance at the Barbican. This is the machine I mentioned, which is called the Lovelace engine, which was a percussion instrument designed for the event. Turning the handle of this represented the training of the AI during the performance. And I'll, with these, just my title, when I was talking about combination, I think I've shown that we started off by engaging people in this discussion of is AI generated or human generated, and we've moved on to a world where the composer is assisted by the AI. It is a co-creative process. And there are 2 sort of tensions in the talk that have played out here. One is the Lovelace music versus maths thing. Here's a nice cartoon from Sidney Patrick from the Funny Adventures of Lovelace and Babbage. Oh, that's all right. Well, I think people can look at the cartoon, and I'll close with that. Thank you very much. Thanks, Dave.
Thank you for your patience, and thank you everybody for your patience. And we'll see if we can find that video for the second half, which you're all welcome to join. So moving on swiftly, we're going to try again with Catherine Higgitt, who is Principal Scientist at the National Gallery in London. Let's see if second time lucky. Catherine, say hello.
Is that working?
It is. Over to you. Thank you very much.
Okay. So my name's Catherine Higgitt, and I'm a scientist working at the National Gallery in London. And today I want to talk to you about how AI is helping in the technical examination of paintings and other cultural heritage artifacts. In thinking about AI in museums, you may be more familiar with the use of AI in understanding our audiences, or in the use of AR and VR as part of a visitor experience. But I wanted to talk about something a bit different, and which those of you who attended CogX last year will have heard about from my colleague Miguel Rodrigues from University College London. But stepping back a moment, why do we undertake the technical examination of paintings? There are three main reasons: to support art historical research, to interpret and contextualise the collection. And so here we might be interested in the materials an artist chose to use, their working technique, the evolution of the design, questions of attribution. To help conserve and care for the collection, so understanding how a painting has changed over time, either through deliberate interventions or just the changes that occur as materials age, so that decisions can be made to help preserve such collections. And finally, to share and present the collection, whether with scholars, researchers, or the general public, in a variety of ways. If we look at an image of a painting, there's a tendency to think of it as a 2D object. However, if a tiny microsample is taken at a given location and mounted in cross-section, you can see that this is far from the case. In this sample, taken from the Virgin's Mantle in Leonardo's Virgin of the Rocks, we see a ground layer, a layer of preliminary drawing, and then multiple superimposed layers of paint, each of which represents an intimate mixture of pigments in an organic binder. Samples like this allow us to very precisely understand and analyse all the materials present at this particular location in the painting and how the various layers were built up. It provides us with a ground truth at this location. However, sampling requires the removal of original material from a painting, albeit a tiny amount, and it's not always acceptable, and it can only tell us about materials present at that particular point. Alternatively, we can use various types of imaging as an entirely non-destructive way to capture information about an entire painting. Depending on the choice of radiation and its depth of penetration, we can see features at or even below the surface of the painting. These approaches are very revealing and give information about where things are spatially distributed across the painting, but not much information about what they are. To try and address both of these needs in a non-destructive manner, a range of spectroscopic imaging techniques are becoming increasingly available and more widely adopted in the heritage sector. These effectively record a spectrum at each pixel across a whole painting, allowing maps showing the distribution of materials over the painting to be created. However, we must remember that we're not just looking at the surface. Depending on the type of spectroscopy and the degree of penetration involved, the signal recorded at each point can include contributions from some or all of the materials and layers at that location. Thus, interpreting these mixed signals to characterise the materials present and to visualise the features of interest is extremely challenging. While signal and image processing approaches have been used before in the cultural heritage field, this has been relatively infrequent and typically addressing very specific problems. But with the increasing use of these spectroscopic imaging approaches, generating huge, complex, multi-dimensional datasets from entire artworks, this is all changing. There are two spectroscopic imaging techniques or modalities that are proving particularly valuable: hyperspectral imaging and macro X-ray fluorescence scanning. With hyperspectral imaging, we're typically working in the visible and infrared range, or with infrared radiation, and technology is essentially that used in remote sensing. We collect a series of contiguous images every few nanometers over the wavelength range of interest. And from this stack of images, it's possible to extract a reflectance spectrum at each pixel that contains information about materials present at and below the surface at that point. With macro X-ray fluorescence scanning, an X-ray fluorescence spectrum is acquired at each pixel, allowing you to create maps that show the distribution of different elements and thus of different pigments and materials and painting materials. These huge spectroscopic imaging datasets, this gives you some idea of the sizes, thus contain information about where materials or features are, so they have a spatial domain, but they also have the spectral domain, providing information about what these materials are. But as these spectral signals may also include information about materials below the surface of the paintings, there is in fact a depth dimension also. With this wealth of complex multidimensional data, the traditional, highly manual approaches typically used in the field to interrogate the simple 2D technical images don't work. We need advanced algorithms and the means to automate data processing. We also need to be able to combine information from several imaging modalities to gain more insight, and to be able to incorporate domain-specific knowledge, for example, when a particular pigment was in use, or information about the exact materials present at a particular location, for example, gained from samples, so incorporating this ground truth information where it's available. With this profusion of imaging data, it's also difficult to capture and to share the wealth of information it contains, so we also want improved means by which to visualize features of interest or to summarize the materials information contained within the datasets. And finally, with the methods currently being used to process these new types of datasets, which derive from the remote sensing or chemometrics fields rather than being designed for the heritage field, there's a strong sense that there is more information available within the datasets than we're currently exploiting. Cultural heritage datasets are perhaps uniquely challenging when trying to develop AI and machine learning algorithms. Materials are combined and layered, and the resulting signals are highly non-linearly mixed. Ground truth is often unavailable or limited because each painting is unique. We don't know what materials were originally used, nor how these materials have subsequently aged, or whether other changes have been made. Because materials degrade or are used in combinations, the signal collected may not match well with those in available reference libraries. And finally, the algorithms we develop really need to be able to combine different data modalities, which may differ greatly in their resolution. Given the particular challenges of our data, we're increasingly turning to AI, machine learning, and other state-of-the-art data-driven approaches to interrogate our datasets. I want now to give some examples of work we're undertaking in this area within the Arctic project, an EPSRC-funded collaboration between the National Gallery, University College London, Imperial College London, and Duke University. At present, when working with hyperspectral imaging data, we typically use tools actually designed for the remote sensing field to determine what pigments or other materials are present in each pixel and to map their distribution. This is labour-intensive, slow, and requires a lot of expert user input. The problems we are tackling are also typically more complex than in remote sensing. We cannot assume linear non-mixing, we don't have this ground truth available, we don't even know the number of end members expected. Given these complexities, we need AI and machine learning approaches which can operate in an unsupervised or semi-supervised fashion. As an example of our work on materials characterization and spectral unmixing, I want to show some work we've undertaken with X-ray fluorescence scanning data to develop algorithms to unmix the overlapping signals from different elements that may be present at a given pixel. So returning to Leonardo's Virgin of the Rocks, from previous work using infrared reflectography, it was known that below the current paint layers there was a drawing for a different abandoned composition. However, this could only be partially visualised, and last year, in preparation for an exhibition at the gallery, further work was undertaken using X-ray fluorescence scanning and hyperspectral imaging to investigate whether more could be revealed about this first composition. Very unusually, the material that Leonardo used to outline this first abandoned composition contains a little of the element zinc. Thus, the zinc distribution map shown here shows a very weak signal coming from these concealed lines and reveals more detail of this first design. However, this map that is supposed to show the distribution of zinc is dominated by the signal from copper that has not been correctly separated from the zinc signal using the standard method to unmix or deconvolute the X-ray fluorescence spectra. The spectrum shows that the zinc peak is a weak shoulder on the front edge of the much stronger copper peak that is very close to it in energy. Gold can also be seen to be close in energy, and if I now overlay these maps, you can see that the copper and gold signals are contributing to the zinc map, making it hard to identify the true zinc distribution. To deconvolute the true zinc signal from that due to the presence of copper or gold, the normal approach adopted requires the user to define which elements are thought to be present, and then the spectrum is fitted with a series of Gaussian curves centered at the X-ray fluorescence lines of each element looking at each spectrum pixel by pixel. Our alternative approach instead adopts a pulse detection algorithm from a totally different field, the field of electronic sensors, to detect the X-ray fluorescence lines with increased sensitivity, and then to fit them with B-spline functions. The detected lines are then assigned to the elements, eliminating the requirement for the user to predetermine which are present. Here we see the results produced totally automatically with our new approach. In a subtle but important way, this map far better represents the actual zinc distribution, and a couple of key differences are indicated here. This new automatic process does not require the user to predefine the elements present, and additionally provides confidence information, allowing very low quantities of materials to be securely identified. Crucial here, where we were trying to detect very weak signals from lines now covered by the blue copper-containing pigment used by Leonardo. In addition to
you can wrap up in the next slide or two.
Characterization, we were also interested in improved visualization of features of interest. In the case of Leonardo, this was the subsurface feature, the underdrawing. The infrared reflectogram and the X-ray fluorescence data has given us a partial image, but hyperspectral imaging data in the shortwave infrared range, after application of another transform used in remote sensing, revealed further snapshots of the underdrawing. In this case, we had to manually trace the glimpses we could see from the hyperspectral data to obtain the image of an angel and baby. But when this was combined with information from the other modalities, even more detail could be seen. This was an entirely manual and hugely time-consuming process. Within the Arctic project, we're exploring AI options to try and do this more automatically. One option when trying to extract
you there, if you've got a couple of sentences, and then we'll have to move on. I'm sorry.
So I was going to talk briefly about the separation, and just to with a double-sided X-ray to show that if you have a panel with two sides, the X-ray is a mix. And we've developed a learning algorithm that takes the X-ray and the two coloured images from either side and is able to reconstruct the hypothetical X-ray for the separated, as if you could separate the X-ray into the two sides, which is very important for conservation processes and to inform our historical research. And then finally, we're now moving on to trying to do a similar separation where you don't have, you can't visualize both sides because these are overlaid images. So there's a male portrait beneath a female portrait in this painting by Goya. And finally, I wanted to thank colleagues at the National Gallery and within the Arctic project, who can be seen here, and to flag a conference that we hope to be running in April next year as part of the conference, hopefully in person, but possibly virtually. Thank you.
Catherine, thank you very much, and we all appreciate our speakers being that little bit quicker, and I'm sorry to put you and the others under pressure. There'll be time in the Q&A for everybody to really get stuck in and find out more. Our technical hitches have not helped anybody. So with stepping up next is going to be Drew Hemment, who is Chancellors Fellow and Reader at the Edinburgh Futures Institute. Drew, thank you very much for joining us. It's all yours.
Thank you very much. Okay, well, it's great to be here. I'm pleased to say I've got something of a treat coming up for everyone here. I'm speaking about the AI and Arts group for the Turing, and also the Experiential AI research and theme at the University of Edinburgh. And we're working with artists, and we've got some live pilot projects. And today, for you, I'm going to present a world exclusive screening of a preview of a significant new artwork by Jake Elwes, one of the artists we're working with. Can we get over to the slides, please? So I'm going to make sure you've got my slides. I'm going to be focusing on one dimension of the Turing group. The Turing group's looking at reciprocal benefits between, oh, hang on a minute, sorry. I've been told to do something. I've done that once, but I'm going to do it again. Okay, the Turing group's looking at reciprocal benefits between the arts and science. And that poses an interesting question. I think for many of us, our minds might go first of all to how artists and arts organizations, archivists, etc., can use AI, machine learning, and other data-driven technologies in their practice. But an interesting question is, what can AI researchers get from the arts? And that is really at the center of a reciprocal focus for the Turing Group. Now, I'm going to present to you a research theme and group up in Edinburgh called Experiential AI. And we're looking at developing a model for machine human learning and development where knowledge is created through the transformation of experience. And this is proposed as a new research theme in which artists and scientists and engineers collaborate to inspire new concepts and paradigms for ethical and responsible AI. And at the core of that vision is the hypothesis that art and tangible experiences can mediate between computer code and human comprehension to overcome the limitations of explainability in AI systems. We're researching this, we're studying it, we're writing about it, we're also practicing it. And we're working with these three artists, and I'm going to say more about their work, and I'm going to go pretty fast so I've got time to speak about their work. And we're presenting an exhibition later in the summer as part of Edinburgh's summer season. When many festivals are cancelled, we're going to be presenting some outstanding digital artworks with artists working with AI. So, context. In Edinburgh, we've got a meeting of two worlds. AI, Edinburgh is one of the first places that did AI research way back in the 60s. And it's also the world's leading festival city. And it's those two, that meeting of two communities and two interests that's really inspired me. I've spent my life working between research on technology and practice in the arts. And I was director of the UK's Digital Culture Festival for 23 years. And many artists in my domain, in the domain of new media art, often working at the boundary between art and design, are very much interested in inquiry into technology and in making technology transparent. This work here, Anatomy of an AI System by Vlad Njola and Kate Crawford, is a wonderful, wonderful piece that delves into the hidden layers involved in an AI system, taken really holistically, and presents that in a very accessible way. Other ways, so we can see that artists are revealing hidden critical issues in algorithmic systems. Other artists are working with algorithms and data as medium. Mario Klingerman, for example, and he talks about the distortions in the image as a Francis Bacon effect. And what we can see there is that the artwork enables the character and artifacts of machine learning to become explicit. And then another work by Trevor Paglen and again Kate Crawford, interestingly an AI researcher collaborating with artists, ImageNet Roulette challenged the bias in a training data set and really had a viral impact. And it led ImageNet to scrub a large proportion of those images and also brought attention to the underlying, really complex political, philosophical questions about what happens when we harvest data at scale and process this data at scale in the ways that we do. So the research challenge, and I'm checking on time because I know I'm going to run short of time, so I might speed ahead a little bit. So the research challenge here, or certainly the question I posed, is what can the arts do for AI? And I'm just going to spend a moment just to think about, well, what are the research questions in AI that artists and this kind of practice could touch on? So one issue with machine learning and deep learning and related technologies is that they're not transparent. We often don't know why they do what they do, why they reach those decisions. And it it's been proven that it only takes a very, very small amount of noise to get the wrong outcome, but with very high levels of confidence. And if you think of that in driverless vehicles, that can have really catastrophic consequences. Therefore, explainable AI is really at the forefront of AI science, but this has challenges. There's not really a common understanding of what explainability is. It's recognized and becoming increasingly recognized that we need to look at the broader socio-technical context.
Drew, if I can give you 2 minutes, and I think, if I remember, you've got something special to show us.
Thank you very much for that. Yes. Okay. Right. Wow. I think time's just become constrained because of technical difficulties. So, so what I'm going to do is I'm going to run through a whole load of slides and cut right to the end. I'm going to quickly tell you about the 2 projects that we have. We're working with, first of all, well, our purpose in the pilots we're doing at the moment is to test ways to dispel the mystery of algorithms and make their mechanisms vividly apparent. We're working with Caroline Sinders and Anna Ridler, 2 leading artists and designers working with AI. Each of them are AI researchers in their own right, but they also have an arts practice, and also Jake Elwes. We've been developing this project over the last year or so, leading to a number of publications, our first exhibition last summer, already we're getting some learnings about how you design these kinds of collaborations. And there's 2.
Drew, you give us this in 60 seconds now.
Okay, two pilots, one by Caroline and Anna, and they're interested in revealing the hidden human dimensions and inputs into an AI system, and also its environmental cost. And they're going to be developing an artwork, creating representations of nature that are mediated by technology, and developing a framework for climate-aware AI. And then Jake Elwes. Jake Elwes has developed a project called Zizi, and here he's looking at the context of drag, where identity, the question of the real, is already up for grabs and challenged. And he's developed a project that's using that site to challenge some mystifications around AI, such as the idea, the anthropomorphism that often surrounds AI, and to question the bias that can be in AI. And I've got precisely 30 seconds left of my 60 when I'm going to give...
You've got less than that, Drew. You've got 5.
Which, if you can play the last film, is a world exclusive for you. With audio, please.
We'll do our best.
We're closer than pages that stick in a book. We're closer than ripples that play in a brook. Wherever you find him, you'll find me, just look. Closer than a miser or the bloodhound's Deliza me. We're closer than smog when it clings to L.A. We're closer than Bobby is to JFK. Not a soul can bust this team in two. We stick together like glue. And when it's a sleeping time, that's when we rock.
Okay, so that's just the start for us. We're looking for partners and collaborators to work with the research team in Edinburgh and the fantastic artists we're collaborating with. Thanks to Jake Elwes. Thanks to you for joining. Thanks very much.
And thank you to you, Drew. Thank you very, very much. Okay, time is tight. So next up, we have Mark Bell. Mark is Senior Digital Researcher at the National Archives. Mark and I are doing a tag team where I'm sharing the slides and Mark is directing me. So let me just get ready. Over to you, Mark, please.
Okay, thank you. I don't know how to follow that last video, but yeah, so if we can start the slides. So I'm talking about machine learning in the archives. Next slide. So National Archives is the official archive of the UK government, based in Kew We're responsible for over 1,000 years of historical documents, and those pictures that you can see kind of probably encapsulate most people's visions of what an archive looks like. But we're actually becoming more and more a digital archive. We have over 80 million digitized documents, which are currently downloadable for free during lockdown. Next slide, please. So the way you would normally access our material is via cataloguing. So we take a document, we may digitize it, someone reads it, and they create a short description, and then you can search it through keyword search. In fact, there's no intelligent search there. Next slide. But born digital is our biggest challenge. We work to a 20-year rule, which means we're receiving documents from government from the end of the last millennium. And if you think back to what the IT world was like 20 years ago, you may begin to understand the challenge we've got. And if you think about how documents may have been filed on hard drives and shared drives, you can understand why we refer to it as the digital heap. And not only is it the kind of disorganization and the general scale, but also there are possibly over 1,000 different digital file formats, and that's growing obviously as time goes on. And then at the other end of the scale, we have the web archive, which is being archived right as we speak, and there's over 200 terabytes of data. Again, that keeps growing. Next slide, please. And so this slide is from our digital strategy, and it just shows the kind of the thinking that we have to think from preservation, contextualization, presentation, and enabling use. And we need to think beyond presenting a single document as we have done for a long time, and now thinking about how we might allow computation over our collections. Next. So I'd like to just talk about a few projects involving machine learning that we've got going on. Next slide. So the first one is Archangel, which I was involved in. And this is combining deep learning with blockchain to underscore trust in digital objects. And the deep learning side was particularly around the reformatting objects. So if you can imagine a video file from the 1990s, it may no longer play, or it could be a HD video that we don't want to download over the internet. So but how do we prove, if we reformat that file to a more modern encoding, how do we demonstrate that we haven't tampered with the video or it's been corrupted along the way? What the partners at University of Surrey were looking at was what they call content-aware hashing, where you can hash an object in such a way that if you change the format, you'll get the same hash again, whereas if anything happens to the video, you'll get a noticeably different hash. Next slide. This is a new project which just started on called Diagram, which is around digital preservation risk modeling using Bayesian networks to model the preservation function. And as you can see, this is a very small part of that Bayesian network, and already it's a very complex area. And digital preservation is kind of in its infancy, and we don't really know where to focus our attention and our efforts in. So by doing kind of empirical studies and bringing in expert knowledge, we hope to be able to target interventions on digital preservation to the right places at the right time. Next slide. And final sort of big project, funded project that's going on at the moment is called Deep Discoveries, and this is about visual search. It's again with the University of Surrey, looking at how we might allow people to search for patterns or similar patterns, for example, and across collections. This is from a scheme called Towards a National Collection. We're working with other organisations, you can see in the slides there, to look for. So it's this. We've got a collection of about 3 million wallpapers and textiles, which you would never be able to describe in a catalogue. So it allows that kind of search across those visual collections. Next slide. Next. Sorry. So this is, I've also been experimenting with handwritten text recognition from Transcribus, who's a big player in that area. And the idea behind this project is we've got a collection of 400 years of wills, about 1 million wills. And we want to not only transcribe them and make them searchable, but turn them into data. Because they're full of people and places and connections and property and wealth, so they're fascinating insight into social history of the country. Last year we ran a small project looking at the interaction between the deep learning for the transcription, and crowdsourcing, because the machine learning will never be perfect, and it's very good at the boilerplate text, but less good at all these kind of obscure places and odd things that people leave in their wills. So we looked at gamification, that kind of thing, to make transcription more exciting for people. Next. And the final kind of area we're particularly interested in building research project around is on something called qualitative spatial representation. This is old-fashioned AI based on logic, and this is partly around being able to identify documents with similar layouts, but it's also about being able to understand the structure of those documents and the process behind the documents. If you think of annotations on documents and all the little bits and pieces that get marked up on documents as they move through the system, and being able to relate those to the original text, for example. Next slide. So now I wanted to just talk about some of the challenges we have around scale. Next. And the web archive is the big challenge. So over the past 10 years, these diagrams show the kind of growth in the number of sites, but what they don't show is the growth in the number of documents and the size of those sites, which are growing exponentially. And it's not just the content of the pages, but it's all the PDFs and images that come with them as well. Next. And so with the web archive, we have to think of it as a temporal data set. That if you look at how it's captured in a snapshot. It's not incremental, it's just periodical snapshots of websites. So we have to think about how people will use it. So they may be looking at how the content has changed over time. They may be interested in content at a particular point in time and want to know how to select that, the right point. They may be looking at the structure, which can tell you something about how information is presented on the web, but also how it may, the structure of the sites themselves change. And then those little diagrams at the bottom are really to demonstrate how concepts or functions of government or topics could emerge, grow, and then move within government functions. Next slide. And time is obviously a big feature.
Mark, 2-minute warning, please.
Okay, right. Time is obviously a big feature. So we have 1,000 years of history, but actually those most recent things, which are the bits at the very top of this graph, the web archive, the Born Digital, are potentially going to swamp the other 1,000 due to the volume of them. Next slide. And so this is just a very small example. I'll focus on the bottom two, which are really, one of them is a description of a policy document. It's called smallpox vaccination policy. And the other one is a web page. And how do we balance between a document where we have a very short human created description versus all of the information, but no short description at all. Next slide. And the final bit we're interested in around AI is the explainability side. Next slide. So in our digital strategy, we talk about managing uncertainty, and we've looked at it with a project called Trace Through Time, but record linkage, and that was our first attempt at presenting some uncertainty rather than an authoritative truth. And now we need to think of it with machine learning rather than just simply classifying things. Maybe we should show the weightings, the probabilities behind the algorithm's decision. Next. And last year we ran an Explainable AI workshop. There's a link to a blog there, which will tell you more about it. But we talked a lot about whether we need, why we need explanations. And I think of 3 levels, kind of explaining the result, explaining the algorithm behind the result, and explaining the process of how you chose and trained the algorithm. Or sort of different ways of looking at explainability. Next slide. I think I've almost made this. So we're teaching people machine learning. We have a machine learning club, TNA. And this isn't to create data scientists. This is to train our staff, archivists, and so on, to get an algorithmic intuition. The picture is them learning to put bits of string between dots to understand decision boundaries. And I want to take them through the whole process of choosing data, training it, testing the accuracy, and so on, interpreting the outputs. Final slide, I think. Final slide. Okay, good stuff. Apart from the swans at the end. And what we want to do here, we want to take those questions from the Explainable AI workshop and put them in front of informed archivists and developers and user experience designers in our catalogues and so on to answer some of those questions around explainability from the archival perspective. And then also to start conversations about how when government systems start to make decisions through machine learning, through AI, how do we archive those? Because they're making decisions that would normally be archived. And how do we then present them in 30, 40, 50 years' time? And then the final slide is the...
Oh, well, maybe we'll skip the final slide. Mark, I'm afraid we'll have to draw things to an end. I'm under pressure. I just want everybody to join me in thanking all our wonderful speakers and the production crew for flexing with us today. And I hope you enjoyed the show as much as we did.
Want access to more CogX videos? Subscribe now for free at cogx.co.